just put it right on your chin. Merci d'être bien assis. On va pouvoir reprendre avec une session avec un orateur invité, donc Jason Donenfeld, qui va nous parler de Wireguard, un outil qui, à mon avis, va intéresser nombre d'entre vous qui en ont marre d'essayer de faire marcher IPsec ou OpenVPN. Et donc, je vous demande d'applaudir Jason pour sa présentation.
Bonjour, c'est Wireguard, c'est un VPN pour le noyau Linux, mais je vais parler anglais, désolé. So I'm Jason, I'm on the internet as the X2C4, and my background is in exploitation, offensive security, finding crypto vulns, finding state machine vulns, breaking lots of kernels. And I wanted to make a VPN that would avoid a lot of the pitfalls I've seen doing offensive security. So a VPN is a defensive thing, but it's been designed very much from kind of an offensive angle at what I've seen go wrong in the field. And so it's layer 3 only. And as we'll see throughout this presentation, a lot of things like that are pre-decided for you. So it's very opinionated. It's only layer 3, it's not layer 2, because I think layer 3 is the right way of designing tunneling through the network. Works for IPv4 and IPv6, as you'd expect, and is designed for the Linux kernel, built in the core of the Linux networking stack. We also have slower cross-platform implementations that live in user space, but for the most part, it's kind of a Linux kernel-centric project. It's UDP-based, so it gets through firewalls in the normal way with stateful NAT. It works with UDP. It's not a separate IP family. And it uses modern cryptography, but also conservative cryptography. We want new crypto to get the properties we're after, but we're not doing anything too fancy, too freaky. As we'll see, the emphasis of the project is being super simple, super auditable, having minimal code base. And as a consequence, we've kind of moved key exchange out of scope of the project. So it has an authentication model a lot like SSH's authorized keys, where each party has a list of each other's keys. And how you get those in the keys file is kind of out of scope of the project. So we want to be able to fit in with lots of other pre-existing key exchange mechanisms. And as Raphael mentioned, it's a replacement for IPsec, but for OpenVPN as well. Okay, so let's begin. So as I mentioned, it's a really small code base. OpenVPN is this massive thing, 116,000 lines of code, plus all of OpenSSL, which is super big. For IPsec, you need both the Linux XFRM layer for the symmetric crypto, and then something like Strong Swan for the key exchange. So you have 119,000 lines of code plus 405,000 lines of code. Soft Ether is this kind of jack of all trades VPN software that has 1 million protocols, is 329,000 lines of code. Wireguard is less than 4,000 lines of code. We're trying to keep it really small and basic, almost like a toy, but still robust for real networks. So in the planetary system of VPNs, we're the Pluto out there. So the interface it provides is super simple. It reuses everything you already know and are familiar with from Linux. So you can add an interface with IP link, and then you just have a normal network interface. You can add addresses to it, add routes to it. You can use IP tables with it. We even do some nice binding between the IP address people are allowed to be in the tunnel and their cryptographic identities, so that you can even use old school Etsy hosts allow and deny if you want. It works with bind in a way that's more secure than otherwise. And so everything that you'd usually have with a network interface, you get with WireGuard 2. It doesn't require any new funky layer like, say, IPsec does. But WireGuard is super blasphemous. We break a lot of the nice, pristine academic layering that we have from things like IPsec. IPsec has this transform table layer that kind of sits separately from the routing table and exists at like several parts of the packet flow. And in some ways, it's really nice and abstract, and it fits in these layering concerns very well. You know, it was designed by a committee of lots of people with different objections, and they came up with this nice transformation table thing. But that winds up being super complicated. They separate the key exchange out to some big user space daemon. And so from WireGuard, we start with this basic building block of the network interface, and we build up from there. So in doing so, we at first get some contradictions, some problems, and we smush the nice layering together. But then with some nice engineering and a couple tricks, we're able to solve the contradictions and actually get something smaller and more elegant than otherwise. So one thing is that the interface appears stateless to the admin. You add an interface, you configure it, and then you just start sending packets. There's no sense of state that's exposed to the administrator. Am I connected? Am I not connected? What keys do I currently have? This is all kind of hidden away. So it's very similar to plugging in an Ethernet cable into your laptop. It's on or it's off. There's an interface or there's not, but there's no state the admin has to know about. And endpoints roam like Mosh, if you've ever used that, where if you have your laptop in one place and you move to another network, it will just work fine. The connection will stay up. You don't realize any kind of reconnection state happening. Or if you're on mobile and you go between Wi-Fi and LTE, no problem. It just kind of seamlessly roams from one to the other. Identities in WireGuard are just static public keys. So we're using curve 25519, as we'll see a bit later, which is just a 32-byte key, which expands to 44 characters of base 64. So just these really short, simple keys that you can copy and paste around. And beyond that, everything else is invisible. You don't see kind of any of the mechanics under the hood. The thing that allows us to do this, to smush these layers together into one thing, is called crypto key routing. And this is really fundamental to WireGuard, where you have an association between the IP addresses that a peer can be inside the tunnel and his public key. You have a one-to-one mapping between every IP address and the peer's public key. So the whole topology of this is that the WireGuard interface itself, the WG0 interface, has a private key. It has a UDP port that it listens on to the internet, and then it has a list of peers. Each peer has a public key. That's its identity, as a required necessary field. And it has a list of these IP addresses inside the tunnel that the peer can be, these allowed IP addresses. It optionally has an endpoint IP and a port. I say optionally because if you don't give it the endpoint IP, that is where to reach that peer on the internet, it will learn it the first time it receives a packet from that peer. So this is how the roaming works. So it turns out that knowing where the peer is on the internet is an optional field because it can just kind of seamlessly learn as it goes. So the essential idea, anyway, is this relationship between the public key and the IP address being bound together. So here we have a server config and a client config. A server config for these two peers, it gives one of them this 10/32 and then /24. And then the other one, it gives a 32 and a /16. For the client config says, I want to trust the server to give me the whole internet, to tunnel the whole internet. So the client is trusting the server to be able to send any IP address within the tunnel, whereas the server only allows the client to be a one single IP address in the case of the 32, or only in the subnet. So it restricts it. So the way this works for sending and receiving is that user space sends a packet. It goes to the normal Linux routing table that makes the normal routing decision. It says, all right, let's go to the WG0 interface. Then Wireguard gets it and says, okay, let's look at the destination IP address of this packet. And now which peer does this correspond to? If it doesn't correspond to any peer, it drops it. If it does correspond to a peer, then it will encrypt it for that peer and send it off. So on the way out, it's kind of like an additional routing table once it hits the Wireguard interface. On the way in, it's a little bit different. We receive an encrypted packet. Wireguard gets it. It's just this big UDP blob. It decrypts it, and then asks, okay, what peer did I just decrypt that for? Which peer's key did I just use to decrypt it? Then it looks at the source IP address of that packet, and it says, if I were going to be sending in the other direction to this peer, to this IP, would I actually choose this peer for it? And if not, then it means that peer isn't allowed to actually be using that IP address, and if so, then it just hands the decrypted packet back up to the networking stack. So on the way in, it's more like an ACL, and on the way out, it's like an extra routing table. So the whole thing makes sysadmin super easy. We know that if it comes from WG0, and it's from Yoshi's tunnel IP address of 192.168.517, then we're certain that it came from Yoshi. We know with certainty that there's no way any other peer could have been this IP. We know that then it's tied to Yoshi's cryptographic identity. So we have this really direct mapping. It's from this IP. It must be from Yoshi. And so you can imagine super obvious IP tables rules for this, where the input interface is WG0, the source address is this 192.168.517, and that's it. There's no need to learn any separate subsystem to do this. Okay, so just before we go further into how this all works, I'll show a quick demo of what it looks like to use, and it should clarify some stuff. Okay, so we have a peer A and a peer B. And peer A first generates a private key with this WG-gen key, a very simple command line utility, makes a new private key, writes it out to a file called private. And now peer B does basically the same thing. And when we cat it, we see it's just this really short base64 thing. Then we can derive the public key from the private key with WG pub key. And you see it just spits it out. So now let's add an interface. IP link add WG0. And now we can add an IP address to the interface. Now this is just normal Linux networking utility. This is nothing new or fancy. We add an IP address. And then we can give it the private key that we just generated with WG set. We set the interface up so that we can use it, and now we do the same thing on peer B. We add the WG0 interface. We'll give an IP address, but this time it's 10.002/24. And we give it the private key that we just now generated. And we set it up. So now when we hit IP address, we can see the various IP addresses that this machine has. First of all, the ETH0, that's like our internet external facing interface, whereas WG0, that's the one we just made. So we have, from ETH0, we have these 192.168 addresses. That'll be our public internet. But anytime we mention a 10.00 address, this corresponds to our Wireguard interface. So now we can tell the peers about each other. When we hit WG, we can see the current state. Each has their public key and their private key. And now we do this amazing key exchange mechanism called copy and paste from Bob to Alice, where we say that that peer is allowed to be that IP. So Bob, from the perspective of Alice, is allowed to be 10.002, and is accessible on the internet at 192.168.1.2 on port 51820. And then we can do the reverse on the other side. We copy and paste the key, and we say, all right, now from Bob's perspective, Alice is allowed to be 10.0.0.1, and the internet-facing endpoint is 192.168.1.1.51820. And that's pretty much it. Now, I copy and paste the public keys here, but you can imagine automating this or scripting this with any variety of pre-existing key exchange mechanisms. If it's a simple casual thing, maybe you like GPG email or Signal Messenger. If you're automating lots of systems, maybe this is part of your deployment mechanisms where you generate keys and then spin up containers places. If you're into LDAP or various databases, it can fit into that. It can be pre-negotiated over things like SSH or TLS. It does not matter. We just have this very simple building block, and from that you can build as complex mechanisms as you want. So now that we've set it up, when we ping, it works. There was like nothing to say connect. We just do it and it goes. And then when we hit WG, we see that, oh, indeed, there was a handshake, all this happened, but invisibly to the admin. We didn't have to tell it to do that. Okay, so that's kind of the gist of WireGuard. It's not a lot more complex than that. I mean, again, it looks like a toy, but it's trying to be robust for big networks. Let's look at what we can do with this and then how it works. So WG is this really small tool, as you saw, kind of similar syntax to the IP tool. And we now have integration into the various network managers. So it's in OpenRC, it's in Nixos, it's now in Systemd Networkd if you're into that. It's in LinuxKit. If you have Ubiquiti equipment, it'll run on that. People are working on network manager stuff, so it fits into a lot of things pretty easily. Some people like to use this small shell script that ships with utilities called WG Quick that takes this WireGuard configuration file, which is kind of normal config file, except it adds a couple things like you can specify the address and the DNS and post down and kind of extra fields, and the shell script will run that and call IP for you. So then you just need to say WG Quick up and WG Quick down. So I use this all day long on my laptop just for starting and stopping tunnels trivially, but that's my shell script. I distribute it because others like it sometimes, but you can make your own shell script just as trivially. It fits really nicely into network namespaces. So a WireGuard interface can live in one namespace, and a physical namespace can live in the other. So you can let a Docker container connect only via WireGuard. You can completely isolate your browser from anything that's not WireGuard. So in the container case, like for Docker, you'd have your container namespace with, with the network traffic from, say, ping that goes out through the WG0 interface. And that container doesn't have any other interfaces. So the only way it knows to access the internet is through WG0. WireGuard then encrypts the packets and sends them over UDP, except the UDP socket lives in your initial namespace that has your real network adapters in it. So in that case, you have a leak-proof container. In the reverse direction, maybe you want to make a new namespace called physical, for example, where you put your Ethernet card and your wireless card. And then for your normal init namespace, the only thing you give it is WG0. So then when you're using Chrome, it can only see WG0 as a possible way of accessing the internet, and so you don't leak any other ways of accessing the internet. You have a super isolated networking stack. Okay, the way that this works to be seemingly stateless, well, of course it's a stateful protocol, is primarily with a set of timers. So we've designed WireGuard from the beginning to be really simple and to try and have the smallest possible state machine. And that's what we're trying to achieve also with these timers. We've tried to make it so that every transition in the timer state machine is accounted for. There are no undefined states, no undefined transitions. And so we mostly have these 4 timers, or these 4 events. User space sends a packet. If we haven't made a session for 2 minutes, then we send a handshake initiation packet. If we don't get a handshake response after 5 seconds, then we send another brand new handshake initiation packet. When we successfully receive an incoming packet that authenticates correctly, if we have normal network traffic to send back within 10 seconds, no problem. We don't need to do anything fancy. But if we don't have anything to send within 10 seconds after having received something, then we send an empty packet. And this is so that on the other side, if they've sent something and they don't receive anything within 15 seconds, they know something's gone wrong or there's been a disconnection or something strange, and so they just send a new handshake initiation packet. They start the state machine over. And so it's really super basic. We're only ever going to be replying to packets if we receive something. Otherwise, it goes silent. And in the cases where we detect something is wrong, the state machine is so small that we just go back to the beginning, just send a new handshake initiation packet. There's a lot of defense and depth coding techniques that have gone into this. It's one thing to write a program and try and use all the defense and depth techniques, but it's quite another to be designing a protocol at the same time where we can make protocol design decisions and cryptographic design decisions that then make it easier for us to use these defense and depth techniques. So one thing is that all the state that Wireguard requires is allocated up front in the beginning. So we don't need any dynamic memory allocation. So this eliminates heap bugs, for example, completely, because we don't need malloc. This, of course, has the corollary of this last point that because we're not allocating any dynamic memory, we're working on a fixed amount of memory. This means that we don't want to be modifying any of that fixed, finite amount of memory in response to unauthenticated packets. So this means that we only modify our state after we're sure something authenticates correctly. And so this not only helps us prevent the use of malloc, but not modifying state in relation to unauthenticated packets kind of eliminates another big class of vulnerabilities. The other thing is that all the packet headers have fixed width fields. We don't have some crazy thing to parse. So with no parsing, we have no parser vulns. The kind of basic principle, but winds up going a long way. Some aspects of this grew out of a kernel rootkit project, kind of researching what offensive techniques look like. What is it like to exfiltrate data from the kernel? How do you maintain persistence in a network without being detected while still having a robust network link? So kind of out of these research questions, it turns out that a lot of the same things that you want for stealth are actually really useful for defense. So we don't respond ever to an unauthenticated packet, which really hinders scanners and service discovery. You just can't look for a Wireguard peer. So you can put all of your sensitive services behind a Wireguard endpoint, and then they just appear invisible unless you have a private key that server knows about. And so we're only ever responding to packets that have the correct crypto. It's also not a chatty protocol. When both sides have nothing more to send to each other, they just stop sending data. And then when they need to send data, they start again. But there's no keep alive that's always happening, that's always keeping it alive. So if you're not listening at the exact time that network traffic is going out, you probably won't notice. So for the cryptography, we use this noise protocol framework from Trevor Perrin, the guy who did the signal protocol. In the design of noise, we work very closely together, and we got this this very specific handshake for Wireguard, this IK PSK2 mode, where we'll see it's just a one round trip handshake. And we have in Wireguard now a custom implementation of that, especially for Wireguard, especially for the kernel, that's really small, about 400 lines. And it has the usual list of nice properties you'd want from a key exchange. For the primitives, we have curved 519, JPoly, SIPHash, Blake2S, and as I mentioned, it's an opinionated project. That's it. Those primitives you see are what you get. There's no cipher agility. The idea being, if these ciphers break, then you'll update. It seems unwise to me to mix in a secure network a bunch of unsecure nodes. I mean, then you have a big hole. So when things are broken, you update, just like any other software. In other words, we're not allowing for some complex negotiation with downgrades and multiple versions, because your systems are only as strong as your weakest link. So we have the nice cryptographic properties. We have a key agreement, which goes along with authenticity. We have a nice property called key compromise impersonation resistance. So if someone steals your private key, of course they can impersonate you to anyone else because they've stolen your identity. But what key compromise impersonation is that if someone's stolen your private key, they can impersonate anybody to you. They can appear as anyone else to you once they've stolen your private key. Wireguard is not vulnerable to that, so we resist that. Unknown key share, key secrecy. We have forced secrecy. There's a new key that's derived every 2 minutes approximately, so that if you compromise the long-term keys at some later date, you can't then decrypt past traffic. There's some limited identity hiding. There's replay attack prevention, but we still allow the network to reorder packets. Because all networks naturally reorder packets, and if we just throw those away, it'd be a major performance issue. But we do not allow replays. And the protocol has been verified in a symbolic model using a nice tool called Tamarin, where now we have a proof that what we're doing checks out well. And I think others are now working on computational models as well. So as I mentioned, the key exchange is one round trip. We have initiator to the responder, sends this handshake initiation packet, and then the responder replies with a reply packet. Responder back to the initiator. Both sides do some calculation, and then they can send transport data with the initiator sending the first data packet. So really basic. It's only one round trip, which means if anything goes wrong during it, we just start over. We don't have to say, oh, we received the first 6 messages, but not the 7th. Where should we go back? Should we retransmit? We don't have any of these complicated questions. We just go back to the beginning and start a fresh handshake. In order to start sending data, we have to do this one round trip handshake. And the key exchange was especially designed to keep these properties we want where we don't need dynamic memory allocation. We don't need to parse anything. And importantly, both sides can switch roles during the handshake. So the initiator can become the responder can become the initiator. There's no client-server architecture explicit in it. So it's really flexible. If one side wants to go first, that's okay. And I think we don't have time to go through all of this, but I will just show this nice thing. If you've never seen it, Diffie-Hellman is kind of really magical. It's really old. It's kind of the basics of a lot of systems, but it's really magic and worth checking out for a second if you've never seen this. We make a new private key, pick some random number somehow. Then we derive from that a public key. So we saw this in the beginning in the video with generating keys. Then Bob does the same thing, makes a new random private key, then derives a public key. With Diffie-Hellman, you get this really cool property where if you do the Diffie-Hellman of Alice's private times Bob public, that's the same thing as Bob's private times Alice's public. Now, you might say that many functions have this property, except what you hope for with something like Diffie-Hellman is that it's really hard to come up with the result of this in a different way, that you actually need either of these to compute the result. And this is again, really basic, but really neat that we've discovered a function that's able to do this. In fact, lots and lots of functions that can do this. So how am I doing on time? Okay. So what we wind up doing for the Wireguard key exchange is each side has their static identity. That's their long-term key that identifies them. Then every 2 minutes or so, we have a new ephemeral key. And we wind up computing the Diffie-Hellman of kind of all 4 possibilities. We do this static times static, static ephemeral, ephemeral static, ephemeral ephemeral. And because of this nice symmetry of Diffie-Hellman, then the static static, static ephemeral, ephemeral static, ephemeral ephemeral, and come up with the same result. We hash it all together, and we get a session key. It's just 1 round trip. It's super simple to implement. 441 lines of code for the whole key exchange, which is a far cry from the 400,000 lines of code or something for Strong's one. And you'll notice there are no certificates. There's no X509. There's no terrifying ASN1 parsers. We just have these really short public keys. You can exchange them through a variety of mechanisms. And then the actual trusted base of crypto during the key exchange is really small and basic. So it goes into this whole idea of being really auditable, where you can sit down and read this in an afternoon for pleasure because it's so short. We also have a kind of a poor man's post-quantum resistance. In addition to this public key crypto, you can optionally mix in a pre-shared key, pre-shared symmetric key. So there's this thing called Grover's algorithm, where you can get a square root speed up basically on symmetric crypto when you do a brute force search with a quantum computer. So we have a 256-bit symmetric key, so brute force with 2 to the 128 complexity, which turns out to be sufficient. And this speed up is optimal. So by mixing in a symmetric secret, then we have post-quantum secrecy. But of course, how you get that secret pre-shared is a little bit trickier. So what some people are doing with this is, rather than just kind of a poor man's PQ security, we have a hybrid PQ resistance where you do the normal WireGuard key exchange, and then inside the tunnel, you can do one of these fancy new post-quantum key exchanges. It's not something we'd want to put into the core of the protocol right now because we don't know which ones are the best. There's kind of a new field to be studied. But maybe you can take 10 of the new NIST submissions. Maybe all of them will be broken. Maybe some of them will be broken. Do a bunch of these exchanges within the tunnel, since you can just use TCP since it's normal network connection. And then you pop this in the pre-shared key slot, and all of a sudden WireGuard becomes post-quantum secure as well, without having to worry about the fact that these PQ primitives are new. Okay, there's also denial of service resistance. It turns out that hashing in symmetric crypto is really fast, but pub key crypto is slow. So we're using Curve 2519 for Diffie-Hellman, which is super fast, but it's still slower than the network. It's still way slower than symmetric crypto. And so you could just overwhelm a machine by asking it to compute a bunch of Diffie-Hellman. It's a problem in OpenVPN or most TLS-based things where you can ask a server to compute a bunch of RSA or a bunch of Diffie-Hellman. And UDP makes this difficult in particular because you can spoof your source address. So WireGuard uses something called cookies to solve this. We're running a bit out of time, so we'll have to breeze through this. But a little history of cookies. TCP has something like cookies, but not quite, where initiator says, do this expensive thing, or start this TCP connection in this case. Compute this ECDH. Responder says, your magic word is galette. Ask me again with your magic word. Initiator says, all right, my magic word's galette. Now will you do the expensive calculation? And this is good because it proves IP ownership. And then you can just rate limit based on the IP to prevent denial of service. But you have to store state. You have to remember that, all right, galette is associated with this particular source IP. And then, of course, you need dynamic memory allocation. And in this model, there's always a response. Do this calculation, no way, but here's a magic word, then you discover the person because they ask you to repeat the magic word. And then obviously the magic word can be intercepted. So this is not something that Wireguard would want. DTLS and IKEv2 have something a little more sophisticated where initiator says, compute this ECDH. Responder says, okay, your magic word is some big hash. Ask me again with this magic word. Repeats the big hash, and then the computation happens. And it turns out that the big hash is a consequence of doing a MAC on the initiator's source IP address using some changing responder secret. So this is nice because now the responder doesn't have to store the state. He can just recompute that MAC to check it using his secret that only he knows. So you don't need the memory allocation, but there's still the property that this always responds to the message, so we lose our stealth. And the magic word can be intercepted. And interestingly, a bit of a problem, the initiator himself can be flooded by just sending the initiator a bunch of bogus magic words back, and then how does he distinguish between the correct one from the responder? So for Wireguard's perspective, this is also kind of a dead end. Just as an aside, another way of doing rate limiting is things like host identity protocol or Bitcoin even, where there's a proof of work. And it's really robust. It's almost perfect because you can make the work necessary equal to the amount of work the server would have to do, or even unequal, make it unbalanced. And then you're directly comparing the computational requirement. But this also creates a problem. What if you have a server that's talking to a million different peers? Now that server has to do all the proofs of work if they ever switch roles of initiator and responder. So I think this itself can lead to some denial of service just by having to compute it. So the Wireguard variant is like IKE v2 or DTLS, except we have two MACs. MAC 1 is a hash of the responder's public key and a handshake message. So if the MAC is invalid, then the message is ignored. Otherwise, if the MAC is there, but the responder is not under load, is not being attacked, then we proceed as normal. If it's not under load, then we start to look at MAC 2. And the reason for this is that because MAC 1 has the responder's public key, this is a proof that at least we know who we're talking to. We already know that someone must be there. So if they do respond with a cookie message, they won't be giving up anything that they didn't already know. So we maintain our stealth property. The cookie reply itself isn't sent in the clear. We're actually encrypting it, but using as a key that same responder's public key. So it's a little bit strange to use as a secret key a public key. But it turns out in this denial of service attack model, this is a sufficient amount of secrecy because we're worried about unmasking someone on the other end. Then we give in the additional data parameter of the AAD stands for authenticated encryption with additional data. So this additional data gets hashed into the authentication tag. We include the handshake message itself that prompted this, so that you can't flood the initiator with a bunch of bogus responses. The response has to actually correspond to a message that he really sent. And then the payload contains the actual cookie, which is the same thing that we saw with DTLS, where it's a MAC of the source IP and a responder secret. And then MAC 2 can just be computed as a MAC of the whole message using that cookie as a secret. So we maintain the stealthiness, and once we have the IP address attribution, we can just do normal token bucket rate limiting, really basic kind of network textbook stuff. And the cookies can't be intercepted by someone who couldn't already mount an even better denial service attack by just dropping packets. And there's there's less of a denial of service attack against the initiator. Performance-wise, Wireguard is super fast. It's in the kernel, so unlike, say, OpenVPN, we're not copying packets to and from user space a million times. We're using this chop-poly algorithm, which is fast on all hardware. AES-NI is super fast too, but only on certain hardware that actually has those instructions. Whereas Cha-Cha is implemented on big machines and small machines alike really efficiently. And in fact, with AVX 512, it might be the case that Cha-Cha is even a little bit faster, at least for now, than AES-NI. Another thing contributing to the high performance is that it's just really small. There's less code. And so is it always the case that less code results in a faster program? No. But in this case, it seems to be so. We're talking about several orders of magnitude difference in code size. It's just doing less. And so we're comparing the measurements. We have some graph for some hardware somewhere that's favorable. And we're a little bit out of time, so we'll skip over this. We've got some nice CI infrastructure. So just to summarize, it's less than 4,000 lines of code. So if you like to read little projects for bugs, this is a fun little one that you just sit down with in the afternoon. It's a lot different than these massive projects where, you know, maybe you pay some company to audit it and they put a whole team on it and they don't even look at the whole code base and they're all exhausted and miserable by the end. This is like a small, fun thing that hopefully we'll get more eyeballs simply by being smaller. It's also easily implemented with basic data structures. It doesn't require anything too crazy. And as I mentioned, the protocol itself has been designed in a way that lets you implement it in a way that is more easily secure than other protocols. There's minimal state. It's super stealthy, so you can put it on the exterior of your infrastructure without having to worry. And there's a lot of things that are kind of opinionated, intentionally limited to force you to make a secure network. It's available for all the major Linux distros. We've got packages everywhere. Now there are implementations for FreeBSD, OpenBSD, macOS. There's even an Android app. There's a paper on this published at NDSS that you can read online. It's open source. This is a GPL v2 project. This is not proprietary software. There's a mailing list, IRC channel. I have this massive bag of stickers, if y'all want some stickers. And there's lots of work to be done. So if the project interests you and you want to work on something, just come find me and there's stuff to work on. So that's all. Thank you.
Merci Jason. On va avoir le temps pour 2 ou 3 questions. Il était en premier.
Thank you very much. You didn't talk about encapsulation. How do you tackle the fragmentation of the packets from the WG to the internet network?
So it's layer 3, which means it's just an IP packet. So we're not concerned with things like retransmission, right? That's like layer 4 and beyond. So we take the raw IP packet, we encrypt it, and we stick it in a UDP packet. And so the MTU of a WireGuard interface, if you're going over V4, goes around to 1440. If you're over V6, it goes down to 1420.
Okay, thank you. And just another question. Do you plan to introduce a kind of DHCP feature or something like if you have a lot of clients, then the server would be able to allocate IP addresses?
So this is not a feature that will ever be in WireGuard core. Like the whole idea is it just cares about this list of allowed IPs. But we are working on some separate software where you'll have kind of a static long-term link local v6 address, and then over that you can negotiate any other dynamic parameters. But that's like a separate thing. It doesn't have to be embedded because we can easily segment these.
Thank you for the talk. May we have your feedback about the difficulties of being included in the Linux kernel tree, and if it is difficult or not, and the way you proceed to.
Sure. So we're working on our submission. The software itself as a module has been available for a long time now. It's gotten tons of testing. It's almost done, essentially. I gave a talk at NetDevConf in Seoul a little earlier with the networking subsystem maintainers, and the main guy who does the networking stack in the kernel just had one question at the end. He said, "Could you submit this sooner rather than later? Because we want it." So I think it'll have some success once we push it out. There'll probably be a couple versions of the patch set as people, nitpick at little things, but I suspect this will go into mainline.
Encore une question?
Thank you for the presentation. I have a lot of questions, but I will resume it by you focus your presentation on the crypto part, but what about the network part? Like the question of the fragmentation, the replay, the packet drop due to QoS, for example, and a lot of things that other solutions like IPsec have a response, but you don't show anything of that in your presentation.
I guess there are kind of several different questions in here. With regards to packets being dropped, on the transport layer, once you're sending packets, the solution of Wireguard is pretty similar to IPsec or any other UDP-based one, where we do nothing. If a packet's dropped, then it's dropped, and that's the same as if you're sending it over the internet. And it's always been up to the higher layers like TCP to retransmit. If you do wind up doing these things where you have like a retransmission in your VPN, and then you have TCP inside of that, and you have two levels of retransmission, you get some really horrible performance. So it turns out the best thing to do with UDP-based VPN is if it drops, it drops. So that's on the transport layer. On the handshake itself, of course, we want that handshake to actually complete. And for this, we're also not worried about retransmission because our state machine is super small. So if we don't get a reply back, we know something went wrong, we just start over.
Je suis désolé, on va continuer la discussion après. Il va falloir qu'on passe à l'orateur suivant. Donc, merci beaucoup, Jason.
Stickers.